Yeah, dear all, good morning. Now our lecture is Gram-Schmidt process. In this lecture, we are going to discuss how to find orthonormal set or orthonormal basis by using Gram-Schmidt process. In last class, we discussed, suppose we take any S is any set, suppose U1, U2, Un. This orthogonal set. This orthogonal set. We will discuss, suppose any vector is a linear span of S, we return V equal to linear combination of these vectors, like this summation I is equal to 1 to n inner product of v comma ui divided by norm ui square into ui. We discuss the same as you can write I is equal to 1 to n v ui by norm ui to ui by norm ui. We can write. Suppose we are taking this v is I is equal to 1 to n v. This is the orthonormal vector. Suppose I am denoting orthonormal some w1 wi, say wi, where wi is equal to ui by norm ui. Yeah, last class we discussed. We discussed another one also. Suppose any vector, suppose, okay, we can take, last class we have taken z, whatever you take. Suppose you can take, okay, v belongs to, we are using here v. V is any vector in v. Suppose any vector, see, we discuss that z minus w, that v minus w belongs to linear span of S span, as w is linear span of S. We know where what is the w? W we are taken I is equal to 1 to n. See, that means we are taking this orthonormal set. When this orthonormal set, what is the w? If it's orthogonal, we have to take this is the w, this one the w. But here is orthonormal. Suppose this is orthonormal set. Yeah, that's equal to we are using last class will equal to r v comma ui into ui. Yeah, this is the one. See, that means v minus w. This is always orthogonal to S, every vector in S. See, it's orthonormal. That means this v minus w is orthonormal to vector. Suppose we take, suppose v dash is v minus w. W means this one. V comma u1 into u1. If take minus of this plus v u2 u2 and so on. The last vector is v un un. Yeah, this is the one. V minus of this thing. This is here. That means v per b is orthogonal to or orthonormal to every vector. That is a linear span of S per b. That means every vector in S set is orthonormal. Now our aim is that finding this type of vector. What are the orthonormal vectors? See, that's the main thing. We use that Gram-Schmidt process. First, we see geometrically what that means. Suppose we are given u1, u2, u3, any linearly independent vectors. So now you have to find orthogonal. If you know orthogonal set, we can find orthonormal by dividing whose length. Suppose if you know orthogonal vectors, orthonormal vector is you have to convert to each vector length is 1. So when these vectors are there, so already we know the projection. Suppose when you are projecting u1 vector u2 onto u1. When I project u2 onto u1, it makes some angle. See, we know this one, this error vector. Error vector is orthogonal to u2. We require u2. That means u2 minus projection. What the projection here? u2 minus projection is u2 comma u1 by norm u1 square into u1. This is the one. See, in this case, the error vector is orthogonal to u2. See now what is the error vector? Yeah, but how to find this one? Suppose in this one we are using. Suppose we want to find orthogonal vectors. Suppose v1 I am taken u1. I need to find v2. That's v2 is orthogonal to v1. If you know orthogonal, we can write orthonormal later v2. See now what is the v2? Suppose I am taking this error vector is v2. So I am taking error vector is v2. This v2 is orthogonal to u1. It's perpendicular. It's orthogonal to u1. It's orthogonal to u1 means orthogonal to v2. I am taking u2 is u2 minus u2 u1 now u1 square into u1. So if I take u1 is v1, that means u2 v1 and now v1 square into v1. Yeah, this is the orthogonal to v2. Now you have to find v3. This v3 is orthogonal to v1 comma v2. How to find orthogonal to v1 comma v2? See that means suppose you take means u3. Yeah, you have to project it to u3 to suppose u1 u2. This is not u1. Yeah, u1 u2. See u1 u2. See now project u3 onto this. Suppose it's a plane. u1 u2 is in plane. u3 projected on plane. When you are projected to plane, we get some error vector. The error vector you take v3. See, when you are projecting u3 onto this plane, this u3 vector is orthogonal to the error vector. That means when you are projecting that one, we'll get the error vector, original vector u3 minus. See, that means u3 minus u3 comma the total you are projecting that one. See, projected to u1 and u2. See, u1 orthogonal to v2. That is u1 is same as the v1 u2. That means you can take this v1 by norm v1 square v1 minus u3 v2 by norm v2 square into v2. Yeah, come here like this one. See, we are getting that vector. We have to find orthogonal vectors or orthonormal. Orthonormal means you have to take this length is 1. Next we'll discuss. See, that means every vector, suppose you want to find the vector, any vector is orthogonal to each one, we take that vector minus this, the common sum of that one. So by using this procedure, we can find orthogonal vectors. If you know orthogonal vector, what the orthonormal? Orthonormal is we take w1, w1 equal to v1 by norm v1, w2 equal to v2 by norm v2, w3 is v3 by norm v3, and so on. You can find that one. So now we'll discuss what is the Gram-Schmidt method. This Gram-Schmidt orthogonalization process. Using this method, we can find orthonormal set. See, let V be an inner product space if the set u1 u2 un is a set of linearly independent vectors in V. I'm taking any set of linearly independent vectors. Then there exists an orthonormal set w1 w2 wn in V such that linear span of this equal to linear span. See, now we are taking this set is linearly independent and spanning. Linear independent span means it's a basis. So that means u1 u2 is a basis. Corresponding to this one, we can find using this process. We can find orthonormal basis because we are finding orthonormal set. It's also linearly independent and spanning. Spanning independent and spanning means it's a basis. That means we can find we can say orthonormal set or orthonormal basis. Now we'll see proof. Let that means let u1 u2 un be a set of linearly independent vectors. We know this given linearly independent set of vectors in V. In V. Now we need to find. We need to construct. We need to construct a set of vectors. Set of vectors. I'm taking set of vectors W1, W2, and so on. Wn, which, which is this set of vectors, which is which is on orthonormal. Which is orthonormal set. Our aim is this one. We have to construct this orthonormal set. Yeah, this one we shall prove. We shall prove it by mathematical induction, by the method of principle of mathematical induction or mathematical induction, or induction simply you can say, by induction method. By induction. Already studied induction, that mathematical induction or principle of mathematical induction. Now how to prove. First step 1. Suppose let k equal to 1. K equal to 1 and set W1 equal to U1 by norm U1. U1 by norm U1. Here U1 not equal to 0 because we are taken as the, because as the set U1 and U2, UN is linearly independent. It's a linearly independent means every vector is non-zero vector. Yeah, this is a linearly independent. Yeah, this one. Obviously, now observe here. Obviously, now this linear span of, obviously, yeah, what is the linear span of U1? The same as linear span of W1. You can observe here, since U1 we can write norm U1 into W1. That means U1 is the some scalar multiple. Scalar multiple of W1. That means a span. This is scalar multiple. Also, so now you have to check this is the orthogonal. Also, orthonormal means the length is 1. Also, you can check now norm of W1 is norm of U1 by norm of U1. That is a 1. Yeah, this one. Hence, true for k equal to 1. K equal to 1 is true. Now, remaining step 2. Let k is more than 1. Suppose I am taken up to k minus 1. Suppose that we constructed, I am taking this a true k for more than, constructed on orthonormal set of k minus 1 vectors. We consider k minus 1 vectors. Let's say W1, W2 and so on, W k minus 1. Such that, how to construct were such that linear span of W1, W2, Wk minus 1 equal to linear span of U1, U2, Uk minus 1. We are constructed like this one. Yes, since we know this one, since the set, what about this one U1 and U2, Un is linearly independent. Linearly independent means this U1 and U2, Uk minus 1 also linearly independent. Independent. Therefore, this Vk It's not belongs to linear span of u1, u2, uk minus 1. So independent means cannot write a linear combination of previous vector. If it's a linearly independent, we can write preceding vectors. Already you know this theory. So now this is not. Now if you have to prove this vk belongs to linear span, that means our job is over. Now we'll see how to write. We define v equal to suppose some vk, some vector v1 v2, like we have to find this vector. This is other one. Vk uk minus uk comma w1 w1 minus uk w2 w2 minus and so on minus u uk uk up to wk minus 1 wk minus 1 into wk minus 1, this one, and we define this one and set. Now we have need to find orthonormal vector. We set wk equal to vk by norm vk. So if we are taken k minus 1 vectors are orthonormal set. Now we have to prove that for k equal for k values up to k minus 1 is orthogonal we are set. Next vector also we have to prove that orthonormal vector. Then our job is over. See now this is the one. Now you can check clearly this is vk is non-zero because vk is a right linear combination of w1 w2 wk minus 1. This is a linearly independent vector. That's why it's a non-zero. Yeah. Therefore, this is the set. We are therefore what the norm k? Norm of this one. Norm vk by vk. This is a 1. Further we have to show that wk is orthonormal to this one. If you show that wk is orthonormal to this all vectors, then it's include the set. That means we can generalize to for every vector. Further, we have to show that wk is orthonormal to w1 w2 and so on. Our aim is this one k minus 1. If it is orthonormal, this include one. Now we take for any integer I. Suppose any integer I, this I is lies between 1 less than or equal to I less than or equal to k minus 1, or you can say less than k. Okay. Now consider. So now you have to prove this wk is orthogonal to every vector in w1 w2 w. That means I'm taken wi. Wi means I is from 1 to k minus 1. That means this is equal to wk. What the wk equal to? Vk by norm pk comma wi. So this equal to let's say w into wi equal to. So that's a wk we write norm vk. We can write this number, you can write outside vi. What the vi equal to? Vi vk. Vk equal to this one. Now write that one. uk minus uk comma w1 minus uk w2 minus and so on minus uk wk minus 1 wk minus 1, this one comma into vi wi. This is inner product. This is equal to 1 by norm vk. This one correct uk UK WI and minus, yeah, UK W1, that means this is a number, UK W1, W1 comma WI. Okay, we write one more step, UK W1, this is a W1 comma WI minus UK W2, W2 comma WI and so on. So this I is rise between 0 to K minus 1. So in between K minus 1 we'll get, say, some I is there. See where, okay, this is W1, W2, W1, W2 is there. UK W, see, UK WI, UK W1, see the W1, U1, W. See in the between that U1, U2, whether W1, W2, next maybe we get in between some WI, yeah, UK, some WI. Okay, see where we have taken I is lies between K minus 1. Okay, that means it's a K minus 1. See now we are taken UK W1, W2 and so on. W1, W2, we may get some WK, WI, WI comma WI and so on minus UK WK minus 1, WK minus 1 to W, that minus UK WK minus 1 interpreted WK minus 1 WI, this one. See now 1 by norm VK, this, okay, this total into UK WI. See now we know this one are orthogonal vectors, W1, WI, all are orthogonal vectors. See now in that one, WI comma WI unit vector, that length 1. That means these all are zeros. This term is 0 because it's orthogonal. This term is 0. This all are term is 0. This term is 1. And this term is 1. This is equal to UK WI. Yeah, UK WI comma minus UK. This is 0. 0. See now that means WK is orthogonal to W1, W2, W up to WK minus 1. Therefore, this is W1, W2 and so on. WK minus 1. You can include WK is orthonormal. This is orthonormal set. Now observe here clearly. Now observe here. See WK. Now observe here. WK is equal to VK by norm VK. VK is this one. Yeah, VK is linear span of W1, W2, WK and UK also. That means clearly you can say clearly WK is belongs to linear span of, that's a W1, W2 up to WK minus 1. WK minus 1 and it's a linear span of UK also. UK. Yeah, so WK belongs to linear span of, see this is linear span of W1, W2 up to WK minus 1 is same as the linear span of U1 to UK minus 1. This one you can write U1, U2 and so on UK minus 1. The same as UK. This is WK belongs to linear span. Also WK, yeah, WK belongs to linear span of this one. UK belongs to linear span of W1, W2, WK. You can see observe here since since from here, since uh, since what the UK equal to, from here UK equal to, you can write VK this and plus this, all are this one, but VK equal to UK into norm VK. That means we can write since UK equal to norm VK into WK plus the summation I is equal to 1 to K minus 1, that is UK WI into WI, this one. Yeah, this summation, it's a plus UK into this plus. The UK is WK into norm VK. That means UK is linear span. Okay, hence, see now UK belongs to linear span, this one and UK belongs to linear span. Both are same. Whatever. Hence, by induction. Yeah, now not only K vector, you can go for general induction linear span of W1, W2, and Wn equal to linear span of U1, U2, U1. Now this thing, yeah, it's a linear span and it's independent vector. That means it's a basis. The orthonormal set is called orthonormal basis for a vector space. This is the way. Okay, remember in this thing. So now you have to find this W1, W2, W3. See, for finding W1, W2, W3, we need to find, it's enough first to find this one. This VK. VK is the orthogonal vectors. This VK are orthogonal vectors. This orthogonal vector will convert to orthonormal vector. That's why, that's thing. Better to remember like this one. Suppose if it given, suppose given set, suppose we write U1, U2, UN is there. Now you have to find orthogonal. This is a linear independent set. First find an orthogonal set. Orthogonal means take V1. V1 equal to U1. Now V2. Now V2 is orthogonal to V1. How to get orthogonal? This is U2 minus U2 V1 by norm V1 square into V1. This V2. Similar V3 is U3 minus, we define this one in proof. This orthogonal vector. U3 V2 by norm V2 into V2. And so on. Suppose some kth one, Vk equal to UK minus, sorry, next minus U3 V2 norm V2 square into V2. This is summation K equal to 1 to, okay, so right, I is equal to 1 to K minus 1. So U3 is there up to V2. K is the K minus 1. This one UK VI norm VI square into VI. This is the one. So the same thing. Yeah, now V1 V2. Therefore, W1 equal to take V1 by norm V1. W2 equal to V2 by norm V2. And so on. WK equal to VK by norm VK. So this set is converted to ortho. This is orthonormal vectors. These are orthonormal vectors. These are orthonormal vectors. This thing. You can go for another way also. This is V1 equal to U1. Or you can set W1 equal to U1 by norm U1. Okay, that one. So now W2 equal to, what the W2 equal to? You have to set U2, V2 by V2. So here V2 we can write another way also. This V2 we can write U3. This V2 we can write another way also, U3. See, this is norm V1 square. Norm V1 square we can write V1 by norm V1 and V1 by norm 1. This one we can write U3 V1. See, we are taking W1 is U1 by norm U1. That is V1 is the same U1. Even you can write double 1 by double 1 into double 1. This one. Similarly, V3 can write U3 minus U3 double 1 double 1. That means you have to find again first we have to find normal vectors, orthonormal vectors. U3 W2 W2. This one you can write. If you know orthonormal vector, directly you can write this way, and so on. Otherwise, first find orthogonal vectors. After that one, divide with each length. Suppose V1 divided with this vector length. It's converted to orthogonal vector, orthonormal vector. V2, this orthogonal vector. Now divide with this length. It's converted to orthonormal vector, like this one. We'll see some example. Example 1. Find an orthonormal basis of, suppose given 1 1 2 transpose 1 minus 1 0 transpose 1 0 4 transpose. Maybe ask orthonormal basis. Find the orthonormal set, or you can say orthonormal set. How to find? We'll see. Solution. See now, this is orthonormal. This is some set. It's a linearly independent set. Must be. It's asking basis means it's a linearly independent set. So let given set 1 1 2 transpose 1 minus 1 0 transpose 1 0 4 transpose. Now let I'm taking u1 equal to 1 1 2 transpose, u2 equal to 1 minus 1 0 transpose, u3 equal to 1 0 4 transpose. This one. Now first find the orthogonal vectors. So now take v1 equal to u1. No, v1 equal finding find okay, finding orthogonal vectors. I'm taking v1 v2. I'm taking this is the orthogonal vectors. Now take v1 equal to u1. So now v2. What is the v2 equal to? u2 minus inner product of u2 comma v1 by norm v1 square into v1. This is equal to u2. What the u2 is? 1 minus 1 0 transpose minus u2 v1. Inner product of u2 v1. That means u2 u1 u2 inner product. This is dot product. 1 minus 1. This 0 by norm v. Whatever this is 0 is same as 0. This is 1 minus 1 0 transpose v2. Now v3. V3 is the, if you can check, this is the orthogonal must be 0 dot product. But this is not orthogonal, third vector. Now what are u3? V3 u3 minus u3 v1 by norm v1 square into v1 minus u3 v2 by norm v2 square into v2. So now u3 is the 1 0 4 transpose. Now dot product of u3 v1. See 1 into 1 1 0 4 into 2 8. That's a 9 total. 9 divided by v1 square. What the v1 is the u1. This same as 1 1 2 transpose. What the v1 square is? 4 plus what, 5 6. It's a 9 by 6 into v1. That's a 1 1 2 transpose minus u3 v2. What the dot product? 1 into 1 1 0 minus 1 into 0 0. That's a 1 by v2 is the square is there. That's a 1 plus under root 1 plus 1 and square. That is 2 into 1 minus 1 0. Now simplify this one. Yeah, this is. Now observe here. See now, this is 1 minus 3 by 2 minus 1 by 2. How much? 1 minus minus 4 by 2. 2. 1 minus 2. That's a minus 1. First element is minus 1. Now second element 0 minus 3 by 2 plus 1 by 2. Minus 3 by 2 plus 1 by 2 is, this is a minus 2 by 2. Minus 1 again. Next third element 4 minus, this 2 to cancel, minus 3. That minus 3. 4 minus 3, 1. 4, this 2 to cancel, 4 minus 3, 1. That means V3 element is, sorry, V3 element is minus 1, minus 1, 1. Minus 1, minus 1, 1. You can check it. See, that is minus 1, minus 1, 1. This must be orthogonal to first vector. See, minus 1, minus 1, minus 2 plus 2, 0. Minus 1 plus 1, 0. See, it's orthogonal. Okay, orthogonal to V1 and V2. Therefore, this orthogonal set. This one. Therefore, orthogonal set is set for the first element 1, 1, 2 and 1 minus 1. Already first two vectors are orthogonal, already is given. But third vector is not orthogonal. That's it. For third vector, we got orthogonal is minus 1, minus 1, 1. These are the orthogonal vector. Now, what is the orthonormal? We get orthonormal. Yeah, orthonormal vectors. What is W1 equal to? V1 by norm V1. Take. W2 equal to V2 by norm V2. What is W3 equal to? V3 by norm V3. We know this is the V1, this is the V2, V3. Hence, this orthonormal vector is orthonormal basis. Is asking orthonormal basis or orthonormal set. Therefore, hence orthonormal basis is W1, W2, W3 equal to what the V1 by norm V1 divided with length. That's a 1, 1, 1, 2 transpose. What is the length of this one? 4 plus 1 plus 1, 6. 1 by root 6. Not square, that square. Norm is square root of that length. Comma. This length is 1 by root 2. 1 by root 2 into 1 minus 1, 0 transpose. Whatever this one length is, root 3. 1 by root 3 into minus 1, minus 1, 1 transpose. Yeah, this is the procedure to find orthonormal set or orthonormal basis. This method is Gram-Schmidt process. It's mentioned in find the orthonormal that we have to use Gram-Schmidt process. You can finding orthonormal vector by, you can mention by Gram-Schmidt method or Gram-Schmidt process. DT. Gram-Schmidt process. This Gram-Schmidt orthogonalization process. Now we'll see another example. Suppose example 2. Suppose it's asking like this: find on orthonormal set in R3 containing 1 to 1. How to find orthonormal set in R3 containing this vector? Now you have to find orthonormal vector. Yeah. Solution: let xyz transfer belongs to R3 such that, see, this orthonormal means this is the inner product is 0. So that inner product xyz transpose into 1 to 1 transpose 0. That's same as the inner product will get x plus 2y plus z equal to 0. Yeah, therefore x y z transpose equal to, now we can write from here, we can write x equal to minus 2y minus z, or whatever you can use. That one minus 2y minus z y z. That means y into minus 2 1 0 transpose plus z into minus 1 0 1 transpose. Yeah. Therefore minus 2 1 0 comma minus 1 0 1. These two vectors belongs to this 1 1 2 1 transpose pair. This is orthogonal, but this now observe here, these two vectors are not orthogonal. Minus plus 2 1. This is inner part is not 0. Yeah, this is 0. You can say minus 2 by the plus 2. This is say, this is two vectors belongs to pair. Other belongs to this one and these vectors are not orthogonal themselves. And observe these vectors are not orthogonal. Not orthogonal. Observe these vectors are not orthogonal. These vectors are not orthogonal. See now you have to find orthogonal vectors by using Gram-Schmidt process. Finding orthogonal vectors by using direct you can find orthonormal vector also. Just we previously we find orthogonal. Now find ortho. Okay, we will discuss orthonormal vectors. Orthonormal vectors by using Gram-Schmidt orthogonalization. Process by using Gram-Schmidt orthogonalization process. So let u1 equal to 1 to 1 transpose, u2 equal to minus 2 1 0 transpose, u3 equal to minus 1 0 1 transpose. Now take this one. Now you have to find orthonormal vectors. So what the w1 equal to? W1 equal to u1 by norm u1. What the u1 by norm u1? That is length 4 6 1 by root 6 into 1 2 1 transpose. And let v2 equal to u2 minus u2 in the part u2 u2 w1 w1. Already we know this is orthonormal vector. This equal to u2. U2 is the minus 2 1 0. U2 w1. U2 w1. W1 is the already this orthogonal, that is this 0 0, that is minus 2 1 0. Therefore w2 equal to v2 by norm v2. v2, this is what the length is 1 by root 5 minus 2 1 0. Now find w3. Now let v3 equal to u3 w1 w1 minus u3 w2 w2. So this equal to u3 is minus 1 0 1 transpose minus u3 w1 u3, this is already orthogonal, this is 0. Now you can check it. 1 minus 1 0 plus 1 0 minus u3 w2 u3 w2 w2 this one w3. See, this one you can write w3 the inner power 1 by root 5 into u3 w2 u3 w2 w2. Yeah, minus 1 minus 2 plus 2 0 0, that's a 2 into it's 1 by root 5. W2 is the minus 2 1 0 transpose. Now simplify this one. We'll see that we'll get minus 1 minus 1 by root 5 1 by root 5, that is 1 by 5 minus minus plus 4 by 5 plus 4 by 5. That means we'll get minus 5 plus 1 by minus 1 by 5. First element is minus 1 by 5. Second is 0 minus second element is minus 2 by 5. Third element is 1 minus 0. That's a 1. That means we get v3 equal to minus 1 by 5 minus 2 by 5 1, or you can write this one 1 by 5 into minus 1 minus 2 5. You can check it, this is orthogonal or not. So these are two vectors, that's a minus 1 by 5 plus minus 4 by 5 plus 1. If you take LCM 5 minus 5 plus 5 0. Now again observe this one. Minus 2 1 plus 1 by 5 plus 2 by 5 minus 1 minus 2 by 5 is 0. That is, this is orthogonal to previous vector. Yeah, therefore w3 equal to v3 by norm v3 is equal to this one by this length is 25. This is cancelled, v3 by norm v3, that length is same. That means minus 1 minus 2 5 over the length 1 plus 4 plus 25 30 1 by root 30. Is it correct? 25 29 30. Therefore orthonormal set is orthonormal set is 1 by root 6 1 2 1 1 by root 2 into 1 by root 5 into minus 2 1 by root 5 into minus 2 1 0 1 by root 30 into minus 1 minus 2 5. This is the orthonormal set or orthonormal basis. See, now observe here, suppose you are changing this vector u1 this one u2 u3, suppose interchange or anything, but orthonormal set is not same. You get different vector, different orthonormal set or orthonormal basis. That basis is not unique, you get different vector. Suppose you are interchange u2 u2 u3, here this vector also different. Yeah, this is the procedure to find orthonormal. Now try this problem. Okay, I write two more problems. Thank you. Stop. Already you know every linearly independent set. We know every linearly independent set, we can extend it to form a basis. Form a basis. That means, suppose if we given any independent vector, we can find orthonormal basis by using Gram-Schmidt procedure. For every for any linearly independent linear independent set, we can find on orthonormal basis. We can find on orthonormal basis for a vector space. For a vector space. In V, we can find orthonormal basis for a vector space. That means every independent set we can extend it to form a basis. Already you know that one. Suppose it's given linearly independent set, we can find a basis. That is, here we can find a orthonormal basis. Already, what the Gram-Schmidt process? It's independent vector. The linear span of independent vector is same as the linear span of orthonormal vectors. Okay, that's why every independent set we can find a orthonormal basis. That's the main thing. Okay, now I'm stop here. Thank you.